Hey there, and welcome to my lesson on parametric equations and plane curves. This is kind of an introductory lesson to things that we're doing in BC Calculus with parametric functions. One of the things that we're going to be looking at is how do we write parametric equations, how do we graph parametric equations, and how do we determine what they look like, on a grapher. Because there's going to be some things that we're going to want to work with parametric equations that they're just going to be too tedious or time consuming to try to do with anything besides a calculator. So here, these are a set of skills that we're primarily going to be practicing in the material for this lesson. So let's take a look here. Now, presuming that you've had some exposure to parametrics in pre-cal, which, is always kind of a hit and miss situation because parametrics and vectors and things like that, they always kind of happen towards the end of the year, and depending on how well the year went, maybe you got to it, maybe you didn't, and if you got to it, how deeply did you get into the material? So parametrics are not something that I expect calculus students to have a ton of just, brimming over with knowledge with parametric stuff. But here, they're telling us that we found that f is a continuous function on the graph and was commonly called a plane curve. Okay, well, one of the things that we want to do with parametric equations is really we want to be able to know where a function, or where a particle, I should say, is going to be at a specific time. And that's kind of what we're introducing here by introducing a third variable, and it's usually time. It's not always going to be time, but that's what we refer to as our parameter, hence parametric equations. Here, let's see, what are we looking at? If x and y coordinates of a point on a graph are given as functions of a third variable, then t, then yeah. So here, this is just essentially showing you how we're going to write our parametric equations. So here, this would be like equation 1, where you have x is equal to your function, and here this is equal to equation 2, where y is equal to a function. And they don't necessarily have to be the same thing. In fact, they really shouldn't be the same thing. So you might see something like here that says x is equal to, I don't know, let's say a line, 3x minus 4. Or here, or actually it should be t, because we're doing it in terms of time. And here you might have saying something that says y is equal to, I don't know, a square root, t minus 4, or something like that. It's just going to be two separate equations where x is equal to something in terms of time, or t, I should say, and y is equal to something, again, in terms of t. Let's see, the curve consists of all points that are going to be made up of the x and y equations, and that is referred to as a parameterized curve. And the parametric equations are parameterization for C. Well, that was a mouthful. All right, so let's take a look at this. Here we're going to actually graph a set of parametric equations, so that way we can actually see what the curve looks like. Let's see, a curve C is defined by the parametric equations x is equal to t squared and y is equal to t cubed minus 3t. Plot the points and sketch the curve described by the parametric equations. And here, this is something that you don't normally do on a graph, but with parametrics, it's probably going to be important at some point. The orientation of the curve, meaning what direction does it go from where you start to where you stop? What direction are you taking on the graph itself? So I'm going to take, let's go ahead and pick a color here. Let's fill in our x values in blue. So I'm going to just basically say for all the x values, I'm going to take that t and just, the value of t that we have, and we're going to just substitute it in there. So negative 2 squared will be a positive 4. Negative radical 3 squared will be just a 3. Negative 1 squared is 1, and so on. So these are the x values that we get for the time value that we substitute into the x equation. Okay, so let's try the y values. So for the y values, I'm going to take the t column, all the numbers in that t column, and I'm going to substitute it into that equation there, t cubed minus 3t. And when I do that, I'm going to wind up getting these numbers here, negative 2, 0, 2, 0, negative 2, 0, and positive 2. So when we graph them, obviously we're going to, start here, start at the first, at the top of the table, and we're going to finish here. And the points, as we plot them, are going to indicate the orientation or the direction that the curve is going. So at 4 and negative 2, we're here, and 3 and 0. And so, here if you want to, you can kind of say this is where we're starting, so you know what direction the curve is going to go. And what do we have? 1 and positive 2. So that looks very linear almost, not quite. We have a bend there. And we have something at the origin at 0, 0. We have 1 and negative 2. 3 and 0, so we're back to that point. And then 4 and positive 2. So this is where we're going to stop. So I'm going to start coming this way. And if you want to, you can kind of put the arrows on there indicating the direction that you're going. Otherwise, just remember the path that you trace with the points. And we have something like that. So we keep going this way. And that's what it means to mark the orientation on the curve. So where we started and where we finished, we'll be able to identify the path that a particle would take over any given value of time for these particular parametric equations. So now we're asked to change the following to rectangular form by forming or by eliminating the parameter and then graph it. Okay, so one of the things that we are going to be practicing, and you'll see more of this in future lessons, is how we can convert a rectangular equation, which is what we normally think of, the stuff that we normally put on our Cartesian coordinates, the stuff that you've been graphing forever. Those are generally referred to as rectangular equations or rectangular coordinates. Well, we can kind of create a set of parametric equations from like a single rectangular function. So if we can create a set of parametric equations from a single equation, then we can go backwards. We can take a set of parametric equations and go backwards and create a single rectangular equation. Okay, so what we're going to do when it says eliminating the parameter, here where it's referring to eliminating the parameter, it's telling you get rid of t. So we have to be able to, kind of look at this almost like it's a system of equations. We want to eliminate the variable t out of the two equations that we have, so that way we just have something in terms of x and y the way we're used to having them. So what I'm going to do is I have to pick between equation 1 and equation 2, meaning I guess the one on the left and the one on the right, x equals something, y equals something. I have to pick one of those two equations and I have to solve it in such a way that I could solve it for t in such a way that I could use it to substitute into the other equation. Now, here's my thinking. Here, I want to take this equation, I want to take this equation and solve for t. And the reason why I want to take the equation that is in terms of x and solve for t is because I like having my equation in terms of y already. we're used to everything being y is equal to, y is equal to. So I don't see any reason to take the equation on the right and try and solve for t. Oh, go away. I don't see any reason to take the equation for y, solve it for t, and then try to substitute for x, and then have to go back and then figure out what y is equal to again. So I'm going to take the equation on the left, and I'm going to solve it in terms of time and see what we get. So start by taking the proportion that we have, and we're going to just say t plus 1 will equal 1 over x. I'm going to square both sides to get rid of the square root here, so it'll be t plus 1 is equal to 1 over x squared. And then we can move the 1 over, and that'll be t is equal to 1 over x squared minus 1, or the other way that we can write it is we can say 1 minus x squared over x squared with a common denominator. And in this case, the common denominator 1 is probably going to work out a little bit nicer when we go back and we do our substitution. So now what I'm going to do is I'm going to take that stuff that I boxed, and I'm going to go to the equation that's in terms of y, and I'm going to try graphing that one now. I'm sorry, not graphing that one, but solving for y. So basically, anywhere I have a t, I'm going to take that expression, 1 minus x squared over x squared, and substitute it. So I'm going to, here I'm going to get y is equal to, have a t in the numerator, so I'm going to say 1 minus x squared over x squared. That is for the t that's in the top, and then I'm going to have a 1 minus x squared over x squared plus 1 in the bottom. Well, to clean up this complex fraction here, what I'm going to do is I'm going to take both the numerator and the denominator, and I'm going to multiply them by an x squared, so we can kind of eliminate the denominators that are here. We kind of want to get rid of those and simplify them a little bit. So if I do multiply the top and bottom parts of that equation by x squared, I'm going to wind up with 1 minus x squared overall in the top. And in the bottom, I'm going to wind up with 1 minus x squared plus x squared when I multiply the x squared and the 1 together. And you can see straight away that these two things are going to simplify. And, you know, anything divided by 1 is itself. So my final equation in terms of y is going to be 1 minus x squared. And that is just a very straightforward quadratic function. We're going to move it up one space and reflect it over the x-axis, and that's it. Now in this case, we are saying that t is going to have to be greater than -1. So we're not going to, so on my inputs here, we're looking at now we have our input at -1 where we're not going to use it, okay? But if we were going to graph this, you know, starting, you know, here's the vertex. So I know I'm going to have a point here. At 2, it would be way down here at, like, say, -4. I think that's about where -4 is. And we would have a parabolic arc like so. And of course, because this is a rectangular form of a parametric function or a set of parametric equations, we can indicate that, you know, starting at when t is greater than -1, it would start at the -1 and travel in that direction. So that is, there you go. We took a set of parametric equations, solved it for t, solved it for the parameter that they gave us, and then did our substitution with that expression so that we could have our one rectangular equation in the form of y is equal to something with respect to x, and graphed it. And, you know, that's pretty cool. I think so anyway, but I'm kind of a math nerd, so who knows. Now, here, this is where things are going to start to get a little bit interesting. Hopefully, we're familiar with some of the trig identities that you've seen either in pre-cal or in different lessons in calculus. Because here what we have is, again, a parametric equation where we're saying, in this case, and I didn't actually pay attention to this. I think this is a typo here on the presentation, because in the notes that correspond to this presentation, theta is actually greater than or equal to 0. So essentially we're looking at something over, one, one complete turn around the unit circle, 2 pi. So what we're going to be doing here is we want to eliminate the parameter, kind of like what we did before. We want to eliminate the parameter. In this case, the parameter is theta, okay? We want to be able to eliminate that so that way we can have something more familiar in terms of x and y only that we can graph. Now, one of the things that we want to try to keep in mind whenever we're working with trigonometry and these types of parametric equations, especially since we're asked to eliminate theta, then ideally we want to be able to identify, can we have a trig identity somewhere, or can we create a trig identity somewhere so that way we can actually eliminate the trig stuff altogether. So if you recall, the most basic trig identity, of course, sine squared of theta plus cosine squared of theta is equal to 1. So if we can come up with something that looks like that, or if we can create that trig identity somewhere, then because it would equal to 1, then that means we could successfully eliminate the theta parameter from this set of parametric equations. Okay, so think about it. How are we going to try to do that? Well, if we want to be able to try and create this equation, okay, we have to be able to get sine and cosine by itself. So that means the 4 that's multiplied to cosine and the 3 that's multiplied to sine, we want to be able to get rid of them. So here, that means we're going to wind up with this x over 4 is going to be equal to cosine of theta, and y over 3 would be equal to sine of theta. Okay, so we have sine and cosine by itself now, but in order to use the trig identity, we have to square them. We have to have sine squared and cosine squared, so we're going to go ahead and square these, okay? And because sine and cosine have to be added together, well, let's go ahead and just square them. If I square them, I'm going to wind up with x over 4 squared equals cosine squared of theta. Here I'm going to wind up with y over 3 squared equals sine squared of theta. So now we have our sine and cosine squared. Now we have to add them together. So let's add them together. Let me go ahead and switch colors here so I can see what I'm going to do. I'm going to go ahead and add these together. So x squared and x over 4 squared would just be x squared over 16 equals cosine squared of theta. And y over 3 cubed is going to be y, not cubed, squared, y squared over 9 equals sine squared of theta squared. And I'm going to just add these together. Okay? So together, these two bits here, sine squared and cosine squared, that just makes 1. There's your trig identity. And by creating that trig identity, we have successfully eliminated the theta parameter. And I'm left with 1 being equal to x squared over 16 plus y squared over 9. And that form of an equation should be familiar to you. That is an ellipse, where the motion that we're going to be centered at 1. I'm sorry, we're going to be centered at the origin. So centered at the origin, according to what we have here, where we're talking about, you know, we have our h and our k values. Here we're at 0 and 0 because we're not adding anything to the x's or the y's or anything like that. And the a value is the square root of the x, so that's 4. The b value is the square root of the 9, that's 3. So that's our horizontal distance that we travel. This is our vertical distance that we travel. So from the origin, I'm going to go 3 spaces up and down and 4 spaces to the left or the right. And here, there's no particular place that I know that I'm starting at. So I'm going to just leave the graph, and that's not a very pretty ellipse, but nobody ever claimed I was, you know, Michelangelo over here. So there we go. That is your rectangularized function from your parametric equations, which in this case gave us an ellipse. So when it's asking you, let's see, can you eliminate a parameter? Essentially, whatever that third variable happens to be, we need to be able to figure out some way to get rid of it. In this case, we use a trig identity. In the previous example, we just used some, you know, basic algebra skills, solve for the parameter, so that way we can use it for substitution. And there we go. So now one of the things that we're going to be doing is we're going to say, okay, well, if we've taken a parametric equation and we have changed it in such a way that we could, you know, have one rectangular equation, can we create some parametric equations? Now here, these are not necessarily going to be coming from a single rectangular rectangular equation, but that is on the horizon. So here, when you're interested in the position, direction, and speed at a given time, you need to parameterize the curve of whatever your normal rectangular function is. So what it's telling you, it says the easiest way is to let x equal time, and then represent y as a function of t. And there you go. Boy, everybody's busy this morning, huh? All right. So let's see where we're at. Represent the equation y is equal to 2 minus x squared using these parameters. Okay. So they're kind of looking at it different. They're completely separating these two things. They're not at all the same. Okay, so we're going to look at x by itself, okay, or I'm sorry, example A by itself and then example B by itself, but both of them are going to refer to using this quadratic expression that we have here, okay. Well, in this case, this first equation here, we can think of this as already parameterized. Here, x is already in terms of it's already isolated, you know, like what we normally think of for a set of parametric equations where we have, you know, x is equal to f of t, and y is equal to g of t. We already have x by itself here, so all we have to do is I'm going to take that value of t and I will substitute it into the given equation y is equal to 2 minus x squared, and I will get y is equal to 2 minus t squared. So that really is all there is to it. So the actual parameter, or the actual parametric equation by itself, the whole thing, is going to be just x is equal to t, and y is equal to 2 minus t squared. We didn't really have to do much in the way of algebra on that one, okay? But that is what the parametric equation would be for the example A on the left. Now example B on the right is going to make things a little bit more challenging. Again, we still want, you know, we still want something that's going to say x is equal to some function, and y is equal to some function, then we still want that. That's what the goal of a parametric equation is, okay? But they're not giving us anything. Now in this case, I guess I should put an m here because that's the parameter that they're giving me. They're giving me m as my parameter as opposed to t. So how can we figure out what this is going to be? Well, this by itself, this is the derivative of y with respect to x. So this is like saying the derivative of y of the given function, which would just be negative 2x. So the derivative of y is just negative 2x. So that means that m here is equal to negative 2x. Pardon me. Well, that means now we have something that we can solve in terms of x. So divide by the negative 2, and I say, you can say like negative m over 2, or you can say negative 1 half m, however you want to do it. And we have something in terms of x now. And now that I have something in terms of x, I can now take that something that's in terms of x, and I can come here and substitute it so I can get something in terms of y. So let's do that. So here I'm going to say y is equal to 2 minus, what do we have? Negative m over 2, this quantity squared. And so that'll give me y is equal to 2, and the negative squared will be positive, so this will be minus m squared over 4. So our two values that we have for our parametric equation here, I guess I'll do this one in blue also. So the parametric equations themselves, the whole thing is going to be x is equal to negative m over 2, or negative 1 half m, and y is equal to 2 minus m squared over 4. And that is our, you know, those are two relatively simple examples of how we can take some kind of given equation and use it to kind of create a parametric equation. Okay, this is the example A where it said x is equal to t. That's kind of like if you don't have anything else to use, you could use that. In example B, they're giving us something specific to do instead. Okay, so let's get a little bit deeper into that material here. The parameterization of a line. So here this is specifically taking a line, whether it is in slope-intercept form or point-slope form, and it's going to show you how we can create a set of parametric equations from one line. Okay. So let's see. Here they're giving us a point and a slope. So a point and a slope, essentially that's going to be like point-slope form, where we could write the equation of a line. And they're showing us that the x value is going to be a plus the values of r and t multiplied together, and y is going to be b plus the values of s and t multiplied together across the domain of all real numbers for time, or for t. Okay, if it's time, obviously we can't have negative time, but anyway. Now, in this case here, where they're showing you that m, of course, your slope, is s over r, where that's going to be like the change in y over the change in x. Okay. Now we're going to come back to those here in a minute, and this is the material that we're looking at is if we have 2 points. So if you were just given 2 points, where before you hadn't figured out what the slope is, you hadn't figured anything out, but between these 2 points, we want to know what would be the parametric equation of a line that contains those 2 specific points. Okay. Well, you can see the equation itself actually resembles somewhat of the point-slope form of a line. So we have the variables a plus t times c minus a, and for the x value, and for the y equation, we'd say b plus t times b or d minus b. And now, we're going to see what these are here in a second, because where they're talking about a and b uh, and c and d and all that stuff, this is like the change in x, and this would be the change in y between the points. So that means like a and b and all those things, those are going to just represent uh, like x or y values or something from the points themselves. So hopefully this will make a little bit more sense when we work through this example. Find the parametric equation for the line where they're giving you a point, 3 and negative 2, and a slope of m is equal to 4. So this is going to be that first example where you have a point and a slope that was given to us. Okay. Well, the point that we're looking at here, the 3 and the negative 2, that is a and b. That's how we're identifying the a's and b's of the material that they gave us. So here, let me just write it down. We're saying that the x equation of a parametric function is going to be of this particular line, or of a line, I should say, is going to be a plus r times t, and y is going to be, in this case, b plus s times t. So we've identified the a and the b values. Now t, of course, is your parameter. Your equation is going to have t in it. So we need to be able to figure out what is the value of r and what is the value of s. Okay. Well, that's what they kind of showed us earlier. They said that m is equal to r over, nope, I had that backwards. Hold on. S over r. R. Okay. Well, in this case, the slope is 4, which would be 4 over 1. So that means s would be 4 and r would be 1. So substituting those things, I'm going to say x is equal to the a value, which is the positive 3, plus the r value, which is 1, so I'm not going to really write it, times time, or times t. I keep saying time, but it's times t. And so for the y equation of our parametric function, we would say y is equal to, so the b value is essentially the y value of the point that they gave us, so that'll be a negative 2. The s value that they gave us is the numerator of the slope, s over r, 4 over 1, so that's going to be plus 4t. And there you go. That's all there was to it. So the next one that we're going to be looking at is going to give us an example. We're looking at, again, we want to be able to create the parametric function of a single line that passes through 2 points P and Q. So in this case, again, we're kind of looking at 2 different points. So here, the first point that's given to us, this is going to be my A value and my B value. And the second point that they're giving us, well, we would just say this would be the C value and this would be the D value. Because what we have for 2 points is we kind of had those generic parametric equations that kind of looked like they were in the point slope form, where we said A plus T times C minus A. And we had Y is equal to, in this case, B plus time, or T. I gotta stop calling it time. I mean, a lot of times it is time, but, and so here we're gonna say D minus B. So we've identified the numbers, what A, B, and C, what A, B, C, and D are, so it's just a matter of substituting here. So here, X is going to be equal to, what do we have? 2 plus T times C minus A, so that would be 4 minus 2. So I'll simplify that and say X is equal to 2 plus 2T. And we'll do the same thing for Y. So I'm going to say Y is equal to, in this case, B is going to be negative 6 plus T times d minus b. So d in this case is negative 3 minus negative 6. So it'll be like plus 6. And we'll simplify that one also, and that'll give me y is equal to negative 6 plus 3t. And there is your parametric, there are your parametric equations for the line that would pass through those two given points, 2, negative 6 and 4, negative 3. Now the last thing that we're really going to be taking a look at is going to be asking us to see, can we do some of this stuff on a grapher? And I'm going to come over here to my computer where I can put this stuff in relatively easily. Okay. So if we move on, they're kind of giving us just some general stuff. Here they're giving you information about the TI-84 Plus, where we have the button that we normally push for X. It actually has several things there: X, T, theta, and N. Those are that's where T would be where if we're using it for parametric functions, and they're kind of telling you how you would get to the a bit how you would take the 84 and be able to graph a parametric function. So if you're using that calculator, try to make sure that you're familiar with it, how you get to it. I'm going to be using an Inspire calculator because it's the emulator that I have on my computer. And let's see, since parametric curves can have loops, vertical tangent lines, and cusps, they cannot be graphed in rectangular form. In our next lesson, what we're about to show you, we're going to explore some of these peculiar features. We're going to look at something called a cycloid. They always have weird names. I always really struggle with remembering the types of names that they have, but um, and let's see here, they're kind of illustrating what we would be looking at it is like an old toy called a spirograph. I'm not sure if you've ever used those. You might want to Google it if you're not familiar with it, but it's kind of like you take a a pencil or a pen or something and you kind of stick it in a hole and you're able to move your pencil around. And as it does, the toy kind of moves in a certain way that it's going to make really interesting shapes, like something that kind of looks like this. So here it says consider the hypocycloid, which I would have never known that that's what it was called, but okay, it looks kind of like, I don't know, like something you'd put on top of your Christmas tree. Uh, let's see. The term hypocycloid means under the wheel. Yeah, the prefix hypo is going to be under something. So let's graph it. Okay. So here are the parametric equations that we're going to graph. So I'm going to come here and I'm going to go ahead and graph them. Now, whatever calculator that you're using, try to be familiar with how you do it, how you get to your parametric settings on your calculator. Now, on the Inspire, I'm going to hit Menu. Now, the notes that go along with this say to go to Graph and then hit number 3, but on mine, parametric is actually the 4th one. So just look to see, okay, well, I want to do a parametric equation here. So you can see now it gives us space to enter two equations, one in terms of x, one in terms of y, with respect to t. And in this case, we're going to go ahead and graph it. So the x equation was 5 cosine t, cosine of t, and then we had what? Plus 3 cosine of, what do we have? 5t over 3. And for the next one, we had what? My mouse was in the way and it was bugging me. Oh, it's gonna make me retype it. Okay. Maybe? Yeah, it's gonna make me retype it. Sorry about that. Okay, so let me try to get my cursor out of the way. uh, 5 cosine of t plus 3 cosine of 5t over 3. And then we'll come here to the y equals line, and we'll put 5 sine of t minus 3 sine of 5t over 3. Now, here where it's talking about like the input, where do you want it to look at? So here the calculator, the default is going to be from like 0 to 2 pi. This is the decimal value of 2 pi. Well, we're clearly going to be going something negative. We've already kind of seen what this is going to look like. So here I'm going to change my lower bound to be a negative 10. And I'm going to change my upper bound. I'll just make that a positive 10. Now this is just going to be the horizontal. So if I wanted to change the vertical, I would have to change the vertical somewhere else. But I'm going to go ahead and hit enter. And so you can see my vertical doesn't fit what we were seeing on the paper or on the slide. But here, there is your hypocycloid graph. Okay, so what it's going to ask us to do now, it says, okay, well, can we graph? And so here again, these are keystrokes for identifying the how you get to the parametric stuff. And again, here, the Inspire CX, well, the emulator that I have is the CX cast something or other. CX2 cast is what it is, I think. So that's why I had to pick a different number for parametrics. But yeah, we'll still go menu 3 for graph and then select wherever your parametric is. And the last one that we're going to take a look at here is, can we graph this particular cycloid on the interval from 0 to 6 pi and see what we get. So let's go ahead and take our calculator. So let me go back to the calculator here, and let's put that one in. So let's turn that one off. I don't need that one. So here, this one gave me, for my x equation, t minus 2 sine of t. Nope. And my y equation gave me 2 minus 2 cosine of t. And we're doing it from 0 to 6 pi. You could come down here and hit the pi button. I'm doing it on my keyboard, so it's just quicker to type pi. The calculator knows what that is. And I'm going to, let's see. Oh, that's what it's going to look like. There you go. That's what it's going to look like. And I need to change my window settings. So that's window to match what we have here. My window settings. Let's go from, what we got? We'll just say -1 or -2 or something like that. -1. And we're going up to at least 20 on the x-axis. And the y values look like they're going to fit. So we'll just go ahead and say OK. And there we go. And that is essentially what you should be graphing or sketching on your function. Now, if we wanted to know the direction, where does it start? That's pretty easy to do. What I would do if I wanted to know where it started and like what direction that it went, I would just change the step values. So in this case, we're going to 6 pi, so I can change this. Let's just change it to 1. And so you can see it's kind of starting at the origin, and it's going to make this curve that's going to loop up this way. And then we can go back and oh, we can make it like a 3, and we can see the progression of the curve, the way that it's going to go. So you can kind of see it's going to make that loopy thing that we had here. So let me just go back one more loop, one more time, and let's go ahead and put it back at the 6 pi that we had, and there we go. So we can see that it would have started here at the origin, and it's going to loop, and then loop, and then loop. And it would keep doing that for as long as we uh, wanted to. We're limiting the time that it's going to be doing that. So when we come back here, you should have been able to see something like that, and we did. So that, ladies and gentlemen, is going to kind of bring us to the conclusion of what we're talking about for parametric equations and plane curves. Uh, Again, we kind of looked at how do we graph a parametric equation by substituting the values of t into the x equation and the y equation and plotting the x and y points. And we can, from where we start to where we finish, we can add arrows to indicate the direction that the curve is moving in. We talked about how we can eliminate a parameter so that way we can have a rectangular equation to graph a function, and how we can parameterize a line if we have a point and a slope or 2 points. So I hope this information was useful, that you were able to get something that'll be put to use later on. But thank you very much for your time. I hope everything is well in your world, and see you soon. Take care.